Um, so we're going to talk a little bit here about chemical bonding, and hopefully this works for you guys. Mainly what we're going to talk about this morning is the concept of electronegativity, and I'm going to have you guys add a few things to your notes because we don't have as much here as I probably need to talk about, so you're probably going to need to be writing stuff in your margins in your notes, so I'm sorry about that. I should have been more organized on that. Um, but where you're going to be filling out on your notes is Roman numeral 3, letter A. Okay, Roman numeral 3, letter A, um, where we're talking about electronegativity. Okay, so electronegativity um, can help us to calculate the type of bond that we're dealing with. So we've talked about two types of bonds so far. We've talked about ionic and covalent. Okay, now that's not the whole story. Something isn't just ionic or just covalent, really. It's more of a continuum where something is either really ionic or it can be really covalent or somewhere in between. Okay, so you got to remember what those two things mean. With ionic, basically we're talking about something like sodium chloride. So you got Na with 1 electron, you got chlorine with 7 electrons, and one of those electrons is completely transferred to the chlorine. Okay, so that's an ionic bond. Um, that's a pretty typical ionic bond that we would talk about. Now, a covalent bond, a good example of a covalent bond would be one of the diatomics, maybe hydrogen we could use as an example here. Okay, so hydrogen has 1 electron, 1 valence electron, 1 electron period. If another hydrogen comes along, also has 1 electron, well, what hydrogen really wants is to be like helium. It wants 2 electrons, okay? And helium's not on um, this periodic table because its electronegativity doesn't matter because it doesn't, well, actually, none of the noble gases are on here because the noble gases, we'll talk about what electronegativity is in a second, but um, they don't really have electronegativity, okay? So these two hydrogens can come together and they can share their valence electrons between them, so then you have what's called a covalent bond. Okay? Um, that's a perfect sharing of electrons between the two of them. So um, they're sharing exactly the same, and the reason for that is they're both pulling out electrons the same. I guess we should stop here and actually talk about what electronegativity is. Okay, so this you probably would want to write in your notes somewhere. So electronegativity is basically the strength Okay, the strength with which an atom can pull electrons to itself. And when I mean electrons, I mean like additional electrons past what they already have. Okay? So one example of that, something that's very electronegative, if you actually look at these values on this chart, this is showing you electronegativity values. So we can assign a number to how electronegative it is. Okay? Fluorine is the most electronegative on the periodic table. It has an electronegativity of 4.0. Um, the reason fluorine's so electronegative, it might kind of make sense because fluorine is in column 17, so has 7 valence electrons. It wants one more to be like neon, so it kind of makes sense that that would be the most electronegative. Everything in that last column, actually, fluorine, chlorine, bromine, iodine, all the way down, they have fairly high electronegativities, okay? Now they get lower as they go down, and the reason for that, we may not talk a ton about that this year, but one of the main reasons for that, just so you know, is because fluorine is smaller than the rest of those. So if you think about fluorine, fluorine has a nucleus, and it has basically two energy levels, okay? So the nucleus of fluorine is not too far away from these valence electrons. It can pull them in close to itself without too much trouble. And that's really what happens in an atom. You've got the positive center, right? The nucleus is the protons and the electrons, and that's pulling the electrons closer to itself, okay? With something like chlorine, you've got an extra energy level there, so now the nucleus is further away from those outer electrons, so it can't pull them to itself as tightly, okay? So that's basically the idea with why fluorine is the most electronegative, because it's the smallest in group 17, um, and the group 17 atoms want just one more electron, so they're going to pull pretty strongly on an extra electron, okay? So that's kind of the idea of electronegativity. Now, if you get over here with something like lithium, well, lithium's not going to pull very strongly on an electron because lithium only has one valence electron. It's in group 1a. So it's going to be much easier for lithium to lose an electron, become like helium, than it is for it to gain 7 electrons and become like neon. So lithium is not very electronegative. It doesn't pull electrons to itself. It actually typically loses electrons when it forms a bond. Okay? So that's kind of the idea with electronegativity. And you can look at all these values and you can get a pretty good idea of how electronegative something is just by looking at it. Now notice the metals have low electronegativity values for the most part. Um, and metals tend to give away electrons when they form a bond. Okay, so that kind of makes sense, hopefully. Um, let's see what else here. That's kind of what it says at the bottom, the caption at the bottom. It says that the trends for electronegativities are the opposite of the trends for defining metallic character. In other words, the more metallic something is, the lower its electronegativity. Okay? So what we do then is if we want to determine is something ionic, is something covalent, then we're going to um, figure out the difference in their electronegativities. Okay? 1.7 to 4.0, if they have a difference between the two elements of 1.7 to 4.0, we're usually going to call it ionic. Okay? So an example, again, I used an ACl before. Na has an electronegativity of 0.9. Cl has an electronegativity of 3.0. So if you take 3.0 minus 0.9, you're going to end up with 2.1. Okay? And that is definitely in this range. So 2.1, because there's a big difference in electronegativity, what that means is the chlorine is going to pull electrons to itself a lot harder than the sodium. In fact, so much so that the chlorine just ends up taking the electron from the sodium. So that's basically what happens there, okay? Now there's another situation here, another couple situations, because it's not, I think I said this before, it's not enough to say just that something is covalent. There's something called polar covalent and then covalent. All right, so I'll go ahead and put both of these up here. The thing is, with covalent bonds, yes, they share electrons, but it's not always, the electrons are not always shared equally, okay? Sometimes they are, sometimes they aren't. It's kind of like a tug of war with those electrons, and whichever atom is more electronegative is going to pull the electrons closer to itself, okay? So again, you have an example like H2, okay? Hydrogen has an electronegativity of 2.1. Well, you take 2.1 minus 2.1, and it's 0. Okay, there is no difference in electronegativity. Hydrogen and hydrogen are perfectly matched, so they're having a tug of war pulling the electrons between themselves. The electrons are going to be right in between the two hydrogens because they're the same. Okay, so that would fall in this nonpolar covalent category. There's an equal sharing of electrons. But let's say you have something like, let's see if this is going to work. Well, that's pretty close. Okay, let's try CO, carbon and oxygen, carbon monoxide. Um, so if you've got something like CO, okay, there's a bond there. Well, the oxygen has an electronegativity of 3.5. The carbon has an electronegativity of 2.5. So you take 3.5 minus 2.5 equals 1.0. So now we're in this range right here, the polar covalent. There's an unequal sharing of electrons. So you've got electrons in between the carbon and the oxygen. Okay? I didn't draw that very well. Hang on. But the electrons are not being equally shared. Really, it's kind of more like this. Okay? The oxygen, it's kind of like this selfish kid who doesn't want to share. Right? So it will share because his parents are making him, right? But he's going to pull the toy a little bit closer to himself just so that that other kid knows, you know what, this is really mine, okay? And that's kind of what's going on here with carbon and oxygen, is that the carbon is not able to pull the electrons as tightly as the oxygen. The oxygen is more electronegative, so it's going to pull the electrons a little bit closer to itself. Now, when that happens, we draw an arrow like this to show that the electrons are kind of going more towards the oxygen at that point. And the reason that we call this polar, if you think about polar, like a magnet has a pole or poles on it, it has a positive and a negative pole, okay? Um, Same thing is happening here. There's not a complete transfer of electrons, but the oxygen is going to be a little bit more negative. That side of the molecule, just a little bit more negative. And this side of the molecule is going to be a little bit more positive because the electrons are closer to the oxygen than they are to the carbon. Okay? It's not a complete 1 minus or 1 plus charge because that's what happens when you have an ionic bond. But it's just a little bit of a positive and negative charge on each end of the molecule. That's why we call it polar. Okay? And so that's the basic idea of what's going on here. Um, so what you have to do is you have to basically figure out when I give you two elements, you have to figure out, well, based on their electronegativity difference, are they going to be ionic, polar covalent, or nonpolar covalent? All right? Let's see what else we got here. Why isn't this working? Okay. Actually, I guess that's it. So now what I need to show you is your homework assignment, the electronegativity homework assignment, and I'll kind of walk you through how to do that, and then we'll go from there, okay? Okay, so on this electronegativity homework assignment, you have an electronegativity chart on the homework itself. I'm going to give you one of those separately so that you'll have that for quizzes and tests. You can use it, and you don't need to memorize these numbers. You just need to know how to use them. Um, so basically, what they want you to do on part A is determine the type of bond that's going to form between each pair of atoms. So the first pair is arsenic and sulfur. All right, so then I'm going to just come back up here, find arsenic. Arsenic is 2.2. Sulfur is 2.6. Okay, so then if I come down here, you always take the bigger number minus the smaller number. So 2.6 minus 2.2 would give us the difference in electronegativities here. It's 0.4. Okay, now if you look back at your notes, anywhere from 0 to 0.5, we're going to call that nonpolar covalent. What that means is the electrons are being shared fairly equally in between the two atoms. So we would say that they're basically sharing equally, okay? And so then you're just going to go through this chart basically in that way. looking at each of the elements, figuring out the difference in electronegativities, and then classifying it as nonpolar covalent, polar covalent, or ionic. Okay? Hopefully that makes sense. The second chart here is a little more confusing. It says determine an element that would form each of the three bond types with the elements given. And it says number 15 is done an example for you. So the first one, basically, the three elements that you're using are on the side here. They're the ones that are numbered on the left side. So the first element is boron, okay? And so basically what they were asking you to do is to figure out what's an element that would form an ionic bond with boron. Okay, so you come back up to your chart. Boron has an electronegativity of 2.0. For an ionic bond, we need a difference of at least 1.7. So in the example, they picked fluorine because fluorine has an electronegativity of 4.0. So that's a difference of 2. So that would definitely be ionic. Okay. Then we have to figure out an element that would form a polar covalent bond with boron. So you come back to your chart. Polar covalent, we need somewhere in the range of 0.5 to 1.7. So they chose sulfur, I think. Yeah, sulfur. Because sulfur is 2.6, boron's 2.0, so that's a difference of 0.6. So that falls in that range. And then for nonpolar covalent, you need something that's less than 0.5, basically. So boron is 2.0, phosphorus is 2.2. So the difference there between those two is 0.2. So that's how they do that. Okay, so then you'd be doing the same thing for calcium. You'll figure out an element that would bond with calcium in an ionic bond, just based on those electronegativity differences. Polar covalent and nonpolar covalent, and then you do the same thing again for sulfur. Okay, so hopefully that makes sense. I will post the answer key to this on Moodle so that you can um, figure out if you're on the right track, and then we'll have a quiz on this when you come into class tomorrow. All right, have a good class. I'll see you tomorrow.